Howdy team, welcome back to Dunkino's desk. How are you all doing today? I hope these past few weeks have been treating you well. In this video, I want to talk about some computational and physical chemistry topics that I don't understand too well. I find it somewhat relaxing listening to a person talk about a topic that I know absolutely nothing about, which is probably why I always fall asleep in chem lectures. I won't be talking chemistry the whole video though, so don't worry. Feel free to play me in the background, or if you are also struggling with computational chemistry for some unfortunate reason, please let me know your tips for learning this topic or criticism you might have about the things I say. I'm just going to be talking about what I've learned so far and what I understand of the topic, which could be completely incorrect. So do not use this as an organic chemistry tutor sort of video. Maybe I'll just define computational and physical chemistry first. Physical chemistry is a branch of chemistry that looks at applying the techniques of physics to the study of chemical systems. That is from Google. Computational chemistry. Computational chemistry is using simulations and models to solve chemical problems, and we can use it to predict molecular structures, the properties of molecules and certain reactions, and we can use that to apply it to experimental data. We've got molecular models, and depending on what we want to model, we can modify things. And the three biggest factors that determine the type of modeling that we need are properties we're interested in modeling, the required accuracy of the model, and the computing power. We have classical mechanics and we have quantum mechanics. Classical mechanics uses Newton's equations of motion to calculate the properties or the interactions of particles in a system, I think. And in quantum mechanics, we use wave equations to get the probability of finding a particle within a volume of space. In classical mechanics, we can treat molecular interactions as pairwise functions, which is interactions only between two molecules, whereas in quantum mechanics, it considers the interactions of all molecules with each other. Our simulation can be influenced by the level of accuracy that we need. In classical mechanics simulations, we can adjust our simulation to include certain interactions and exclude others. However, when we make these changes, we have to choose appropriate approximations depending on the environment that our system is in and the problem we want to solve. Okay, we have four basic choices that we need to consider in molecular dynamic simulations. We have the degrees of freedom, so what particles we want to include in our system, the interactions of the particles, boundary conditions, and generation of configurations. I don't know what that is. I built a house on another island, but I didn't realize how far this island actually is. So enjoy this traveling time lapse. Wow, this guy's nice. These shaders are great. We could choose to model a system that includes all of the atoms, including electrons and nuclei. This would be close to physical reality, but it would be problematic depending on what we need the simulation for, because it requires higher accuracy and more computing time. We could also simplify our simulation by using a coarse-grained model where multiple atoms are represented by a single atom. This leads to more simple calculations, but it's not as physically accurate. Okay, so we've got a model. We can simplify it depending on the level of accuracy that we need, which makes it easier to search for energy minimas, but in doing so, we're smoothing the potential energy surface of our system, so we get further away from physical reality. I built this house a couple months ago, but I don't have any footage except for this, which is from a stream. So enjoy this edit I made of my house. I hope you enjoyed that work of art. I used way too many transitions in that edit. I'm sorry. I don't know why I decided to let my horse run free, so I spent the rest of this day looking for my horse. He better not be dead, I swear. I think its name is Peppa? Yeah, Peppa's my horse. Just gonna ignore that sheep there. Why would he leave me? Does he not remember all the good times we've had? When I tried to tame him without an apple, does that mean nothing to him? I searched the whole island until I saw a horse. Sir, you were here this whole time? Do you know how long I searched for you? Oh my days. Okay, back to chemistry. Our particles interact using electron orbitals. All interactions between atoms are due to these electronic orbitals. These interactions can be approximated using bonds, angles, and dihedrals. I think I was wrong about the degrees of freedom stuff from before. It's not what particles we choose to include, it's the bonds, angles, and dihedrals, as in how will we allow the molecule to move in space. We have both internal and external degrees of freedom. Our internal ones are the ones I mentioned before, bonds, angles, and dihedrals, and we have external ones which include translational and rotational motion. When we simulate a molecule, we are essentially seeing how the molecule will change its structure and its configuration over time. A molecule can have several configurations, where some have a higher potential energy and others have a lower potential energy. Say if we wanted to get the potential energy surface of a large system, we cannot find all possible configurations when considering that each atom has a minimum of 3 degrees of freedom, because this becomes computationally expensive. So not only do we have internal degrees of freedom and external ones, we also have non-bonding interactions such as charge-charge interactions, dipoles, van der Waals forces, hydrophobic effects, and hydrogen bonds. Since we have so many interactions that are possible in our simulation, a way to make the simulation more computationally cheaper is to introduce cutoffs. This is, I think, at what distance the non-bonding interactions between our particles become negligible, so that we don't need to calculate these in our simulation. The size of what we are simulating affects what calculations we do. For example, if we wanted to simulate a cellular membrane, we can't really use quantum chemical calculations because the movement of each individual electron is not as significant. This is because in our cellular membrane, the bonds aren't really changing. So in this simulation, we can use approximations on these electronic effects. But if we are simulating a reaction, then we have to consider these electronic states. So sometimes we can ignore electronic effects, I think, and other times we can't, depending on what we're simulating. We can't effectively simulate a cell membrane using quantum chemical approximations and quantum chemical theory due to the size of the system. That is why classical approximations are better for these larger systems. But there are factors that we have to consider when making these approximations for our model. This includes ensuring the model is representative of the system, that the model is computationally efficient, and that the model is extendable, meaning it can be used to describe a range of systems and new domains. Let's use an example of a branched alkane in water. When we model something, we need to think about what degrees of freedom allow the molecule to change its shape and interactions between the molecules. So as I've mentioned before, we've got bonded and non-bonded interactions. And in our alkane in water, we've got bond stretching and compressing, bond angle bending, bond rotation, and in this particular simulation, let's say we wanted to maintain the planarity of certain bonds. We put these effects into our simulation using some sort of mathematical term, apparently, according to my lecturer. I don't know how we do that though. These are our degrees of freedom in our molecule, which help to describe our molecule's conformational flexibility and its movements. For our non-bonded interactions in this particular simulation, we have electrostatic interactions as well as van der Waals forces. By setting these parameters, we've made our quantum chemical calculations a lot simpler, which means that less computing power is required to find energy conformations. So we've established that if we want to model more complex systems like peptides or cell membranes, it's pointless to consider down to individual electron movement. Instead, we look at larger terms like covalent interactions to aid in our modeling. And we can integrate these terms into our simulation using maths and approximations. The first covalent interaction term we have is bonds. To model molecular bonds, we can use either a Morse potential or harmonic potential. The graphs of these two different approximations show the potential energy for molecular vibration as the distance between two atoms increases. The Morse potential is a more accurate approximation for bond breakage, but it's computationally expensive, whereas the harmonic potential is more commonly used in classical simulations as it's cheaper. If you graph the two potentials together, they look completely different. However, in most simulations, the cheaper approximation works because we never actually get to energies that are high enough where we see the two graphs diverge. So on a large scale, the two look very different, but for most systems where the energy is very low, we don't lose any accuracy by using a harmonic potential for bond breakage. Also, when I say computationally expensive, I think what the lecturer said was big calculations like exponentials and stuff like that, I'm not too sure, is a more difficult calculation, I think. Next is the approximation of angles. Again, we use a harmonic oscillator to simulate bond angles. The equation we use to calculate energy includes an equilibrium angle, the current angle that we have, a force constant that gives the curvature of the potential, and then we sum all of the angles together, which gives our potential. Next, we have dihedrals. We represent these with periodic functions. So as the dihedral angle along a bond changes, we get either an increase or a decrease in energy. The final covalent term we need to consider is improper dihedrals, which is used to describe the planarity and chirality of a molecule. Like most of the other covalent interactions, we use a harmonic potential. For this interaction, the terms in the associated calculation include a force constant, which determines the restraint we have on the molecule, a reference dihedral, and the current dihedral angle. So those are our bonded covalent interactions. Let's see how we introduce non-bonded interactions into our calculations. First are charge-charge interactions. We use the Coulomb potential to represent the interactions between two charged particles. In this calculation, we say that our molecules have specific point charges, which mirrors the theory of electronegativity. So a more electronegative atom has a more negative point charge. But charge-charge interactions are often longer range interactions, so it's important that in our simulation, we're not introducing a cutoff that's too early between interactions, as this can lead to inaccuracies in calculating the total energy. Next, we have van der Waals forces. In this interaction, we have a repulsive interaction and an attractive interaction term. The potential commonly used to model van der Waals forces is Lennard-Jones potential. The Lennard-Jones potential uses two terms, sigma and epsilon. Sigma represents the radii of our atoms, and epsilon is the maximum attractive interaction energy between these two atoms. And those two terms make up our non-bonded interactions between molecules in our system. Once all of these terms in our system are established, we add the potential of the bonded and non-bonded interactions to get the total potential energy of our system. Once we put all these terms together, they form what we call a force field. So what forces in our model will be applied. And these help to maintain the structure of our molecule and determine what interactions will be present between our molecules. Let's apply this whole force field thing to an example of phenol, an aromatic ring with a single hydroxy group attached, and let's parameterize it. First, we have to think about what molecules to consider. We have 13 atoms in total, but due to the molecule's symmetry, we only need to consider 9, because only 9 of them are unique. This is helpful in reducing the amount of calculations that we need to do. First, let's go over the non-bonded parameters in our molecule. First, we have point charges, and we have 9 point charges corresponding to each atom. Next is van der Waals forces. So this uses a Lennard-Jones potential, and we have 18 parameters for this potential because 2 values are needed to calculate van der Waals forces for each atom, the 2 values being epsilon and sigma. Now for our bonded parameters, we have bonds. We have 8 bonds, so 16 parameters because 2 values are required to calculate each bond. Next we have angles. We have 9 angles, which means 18 parameters, which also needs 2 values to calculate. We have dihedrals, and there are 4 in our molecule, so this means we have 12 parameters corresponding to dihedrals because 3 values are required to calculate each dihedral angle. This gives us 73 parameters. Now this doesn't sound like a lot for us, I guess, if a computer is doing it, but if we're doing a whole simulation of it, I guess it is a lot, so we need to simplify this. Although we have 9 charges for each unique atom, we can say that each carbon and their attached hydrogen have the same charge as other carbons and hydrogens. So this reduces the number of Lennard-Jones interactions to 4. Using the same process of treating each carbon and hydrogen as similar means we reduce the number of parameters for our calculation down to 39. Now that's still a lot of parameters and it could take a while to simulate, but lucky for us, there is a whole database of molecules that are already parameterized and are ready to be simulated, kind of like online shopping for online molecules. And people actually find the parameters and values needed to describe and simulate these molecules. And there are different approaches to parameterizing molecules. First, we have the bottom-up approach, which is commonly used in quantum chemistry simulations because it considers individual electrons, which makes it a much more physically precise model of the atom. Next, we have the top-down approach, which takes properties from systems we can measure experimentally, and we set parameters that can simulate these properties. For example, setting the bonds and angles of a molecule to simulate it in its crystal form. Now, this doesn't necessarily mean we get a full picture of the molecule. There's pros and cons to both parameterization approaches, but I don't really want to go into it because I don't really care, to be honest. I just hope it isn't a question on the exam. So how do we measure properties for molecular models from experiments? For bonds and angles, we use crystal structures to get equilibrium distances. And we can also use IR to get the dynamics of the bonds and angles. We can use this to determine how steep the harmonic approximation should be to represent these 2 degrees of freedom. And for dihedrals, we can use NMR. Don't ask me how. I couldn't really understand when the lecturer was explaining, so I'm not too sure. Also, we say that our 1,4 interactions are non-bonded interactions, even though in the molecule they are bonded. So we have a strong dependence on the dihedrals to the values we set for our non-bonded interactions, whereas for the bonds and angles, they aren't really dependent on other terms. For non-bonded terms, our partial charges and van der Waals forces are both highly correlated. So we have to be careful in setting the parameters for these interactions. For partial charges, we parameterize this using quantum chemical calculations. And for van der Waals forces, these interactions are parameterized by measuring an atom's solvation properties. Let me try and explain this a bit more. To get the atomic partial charges using quantum chemical calculations, we have 2 methods. The first being we measure the electron density of a molecule as a whole and then assign the whole molecule a charge. In the other method, we calculate the electric field strength at multiple points around our molecule. Then we use maths to find the best partial charge that fits our molecule at each point. Okay, I'm genuinely not understanding anymore. Let's go back to our phenol example. Using both methods, we get slightly different values for point charges, and this is going to have a huge effect on measurable properties if we simulate many molecules of phenol. For example, the amount of attractive force between the molecules will be very different between the 2 methods due to the slight difference in point charges. For our Lennard-Jones interactions, it's kind of the same thing. If we want to calculate macroscopic properties like liquid density and heat of vaporization, the values we use for sigma and epsilon in our Lennard-Jones calculation impacts the values that we get for our properties. Okay, I mentioned force fields before, which is the parameters for the forces that will be applied to our molecule, and these help to calculate the potential energy of our system. And people have made different force fields, so different force fields exist, all with various ways that parameterize the forces, and different ones are designed to be tailored to various properties, and of course some are more computationally cheaper. I think in the past 20 minutes or so, I've covered generally choices of individual particles, degrees of freedom, and how we can represent their interactions. Okay, that was a lot, but there's still so much more that I need to understand. These lectures go for 3 hours each sitting, and I completely zoned out for the first module that I had for this course. I didn't like the professor at all, and the fact that they were 3 hours long does not help. I've compressed almost 5 hours of lectures into 20 minutes. I doubt that this sort of video will get a lot of attention, but it's actually really helpful for me. Who would have thought that rewatching my lecture and taking summary points would be helpful? And I've managed to add little windows onto the side of my house and build a little dock on this island. I managed to find my horse a friend, but it has to be the slowest horse in all of Minecraft history. If you're still here after 20 minutes of quantum chemistry, thank you. And I'm sorry you chose to listen to that. And please, if you understand quantum chemistry, please tell me all the mistakes I've made in this video. In my next Minecraft video, I plan to build a copper golem house, so make sure to subscribe if you want to see that. Make sure to take care of yourself, go drink some water or do something healthy. Take it easy. Toodles!